Bergson and the holographic theory of mind. This will be part 45C, part of the 45 series with the quantum mechanics discussion. We'll be looking at black body, ether, and waves, or the black body radiation problem, where it was first begun to be perceived that waves have a problem with energy transmission, or the beginning of the end of waves as the medium of energy transmission, and Planck's solution of quanta. But we'll be looking at Kessler's solution, which still says waves and ether does the job. It gets a little more complex with modes, probabilities, the ultraviolet catastrophes, the standard physics account that we see. And still we're going to see that a wave explanation could hold, that it cannot be ruled out. So we visited the nature and components of quantum mechanics measurement problem, the form and merits of Bohm's pilot wave solution, its relation to Bell and his inequalities, and the mistaken hang-up on Bohm due to special relativity, which is to say, the sad misuse and non-comprehension of special relativity. Bohm's is in a real sense, a wave explanation of quantum mechanics. It seems to rely on a substrate, a medium for the waves, an ether. It's worth it now, I think, to visit the very origins of quantum mechanics. Planck and the black body radiation, or the origin of quanta, and Einstein's explanation of the photoelectric effect using Planck. It was these, particularly the photoelectric effect, that appeared to destroy the wave theory of energy transmission, and the ether underlying these for waves actually don't exist. They're only a disturbance in a medium. De Broglie noted that Bergson had created a zeitgeist, a wave conception of matter. And this, De Broglie stated, was in the background of his mind in his own formulation, where a particle or any object, an object has a wavelength. Before 1905, energy traveled in waves, and waves were simply a disturbance propagated in the medium, and the medium was the ether. Yet the received view is that in 1905, Einstein destroyed all this with two blows, special relativity and the photoelectric effect. Special relativity explained why no ether flow could be detected in the Michelson-Morley experiment, supposedly. And the photoelectric effect used Planck's notion of quanta, now embodied as photons, as little bullets of energy, and these little bullets needed no medium, no waves to travel. They were not a disturbance in a medium. The base source of this started it all, the black body radiation problem, a problem perceived with the wave theory of energy, and Planck's use of quanta, breaking with the wave explanation, apparently of the black body. So the black body. When a non-luminous body is heated, it gives off energy in the form of infrared waves. Eventually, it will emit visible waves. The energy content, the intensity of the energy, can be measured, falling as on a filament of a device called a bolometer. This, on the right, is the general shape of the curve for a given temperature. On a little graph there, we know we have three curves, one for 600 degrees, one for 601, one for 602. So we have increasing temperature, and the higher the temperature, the higher the intensity of radiation. So again, looking at our little graph there, the energy intensity is the vertical axis, and the energy is increasing, getting higher on that scale. And there's a peak for each of those curves, and that peak is shifting a little more along the horizontal axis, or the frequency dimension. So again, looking at the horizontal, we're going from left to right, or right to left, from lower frequency to higher frequency energy, but inversely, we're going again from right to left, from longer wavelengths to shorter wavelengths. So the apex is shifting to the left. That is, the wavelength of the apex is inversely proportional to the temperature. This is known as Wiens Law, or more precisely, Wiens Displacement Law. So the drop on the left also is becoming increasingly steep. So each wave carries a certain amount of energy. The higher the frequency, the greater the energy carried. So a little picture there, much higher frequency wave in blue, higher energy, much lower frequency wave, lower energy. So starting from the lower frequencies, the intensity should continuously rise, but not. Note, it's falling after the apex. So something seems wrong with the wave theory. Wave theory appears not to work. Planck was given this problem as a student and told, solve it. In other words, his thought was intensified and clarified because this kind of ultimatum tends to make things happen clearly. He began to reason perhaps energy is carried by unit individual particles, termed quanta. That's what he called them. These vary in size according to the emitting source. The source he termed a vibrator. The quanta grow larger with the frequency. Waves, well, not. So the frequency is that of the vibrator. So something about increasing frequency increases the size of the quanta. Intensity. This is determined by the size and number of quanta. The energy, E, increases proportionally with the frequency of the vibrator. So we get Planck's famous formula, E equals h nu, where h is a proportionality constant. This is Planck's constant. Nu, the little v there, nu, is kind of an n actually. So it's frequency. So the energy is proportional to the frequency, where the proportionality constant is h. So why does a curve fall from the apex? Well, the answer in Planck's framework is that the number of quanta, n, is growing less, though the size of each quanta is still growing, where size is equivalent to carries the amount of energy. So what constrains or decreases n? The number of quanta. E equals h nu is only part of the curve explanation, so hang on. Now the foregoing we just went through is Kessler's description of Planck in his book The Energy of Space, 1961. He thought the decrease in n, that is the number of quanta, was ad hoc, a bit arbitrary. Not exactly, we'll explore this in a bit. To Kessler, a wave explanation is still available. If a body absorbs more energy than it radiates, its temperature rises. At a steady temp, absorption equals radiation leads to equilibrium, or implies equilibrium. In wave terms, equilibrium is the number of waves incoming is equivalent to and equal to the number of waves outgoing, energy going into the box, leaving the box. So increase the temperature by 1 degree. A particle, there's a little particle in the box, absorbs more energy and radiates more energy to attain a new equilibrium. The energy increase is proportional to the 1 degree temperature rise. So at 0 degree temperature, to go to the end case, there's 0 energy emitted, 0 frequency of vibration. At a 1 degree temperature rise, the particle is at an equilibrium. It absorbs and emits a certain amount of energy, E, as waves. The radiated E is proportional to the frequency of vibration. It is proportional to the number of waves. The higher the frequency, the greater the emitted energy. So and E gets bigger. Energy grows with the smaller frequency. So far, all in accord with Wiens' law. Energy, E, is directly proportional to the frequency and to the temperature. Now, in a heated body, there's a mass of such particles. There's a little black body shows up there with the little yellow particles in it. all achieving new levels of equilibrium at various rates. By rates here means they get to the equilibrium state at various times, at various speeds, each radiating different amounts of or wavelengths at a given temperature, each emitting a wavelength inversely proportional to the temperature. So the apex represents this, the same vibrator particle at different temperature levels. So as that one vibrator particle moved, we've got circled there from 600 to 601 to 602, its peak was shifting. The same vibrator particle at different temperature levels, an ideal particle as it were. The wavelength only of the most energetic radiation is inversely proportional to the temperature. So as temperature rises, the frequency of the ideal particle is increasing, the wavelength thus decreasing. Are some particles in the body absorbing more than others? Well, the answer is location, 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 or position. Inner particles do not receive as much energy as the outer particles. The apex is not representing particles emitting still shorter wavelengths. These extend to the left of the apex, left of the peak. Why is the curve receding or dropping left of the peak? For some reason, we'll see in a second, there is a decrease in the numbers of vibrating particles. The numbers of vibrating particles in each of the groups comprising particles to the left of the apex, where these are still recording on an instrument measuring in the infrared. Kessler's thesis, left of the apex, groups of particles are still radiating in the infrared. That is in that whole band there from 16 to 25 angstroms. Other groups are now radiating beyond the infrared in the visible range, in the 4 to 7 angstroms. These latter groups are no longer registering on the bolometer. The total energy radiating for any given wavelength is the product of the number of particles and the frequency in each group. The frequency is increasing from the apex, for the number of particles in each group is dropping as particles start radiating in the visible range. Kessler was not sure why Planck rejected this. From the literature, I can't tell if physics accounted for this energy in the visible aspect or not, say by some other forms of measurement, or the bolometer is actually more sensitive than Kessler thought. Something to that nature, but to come it may not matter with respect to a wave explanation. But first, what was Planck's vibrator particle to Kessler? How does it tie into Planck's E equals h nu? For Planck, the amount of energy contained in each discrete packet or quantum is always proportional to the rate of vibration. That is, E over nu is equal to h, where h is the proportionality constant. But why should E over nu always equal h? Planck's h is another of those constants of nature, an abstract mathematical limit. Does it have any concrete physical significance? To disturb the ether, a vibrator particle must be intimately joined with the ether. If the particle moves, it must be capable of dragging the ether with it forward or backward. The motion of the particle is a vibration. The motion of the ether is a waveform. Every vibration, a to and fro displacement, imparts a quantity of energy to the equal to h, to the ether, which enters into the formation of a wave. Each wave requires a quantity of energy, h, to be formed. This quantity, h, times the number of waves formed per second by the vibrator, is the amount of energy E emitted by the particle per second. So fundamental, every wave in the ether requires the same amount of energy to be formed. Why? This is due to the elasticity property of the ether, an expression of the continuity, the oneness of the ether, and present at every point in the universe. This underlies the maximal velocity of the wave. We have the equation v for velocity is equal to the square root of L over d, where v, velocity in a medium, L is the elasticity, and d is the density of the medium. This would be a rational basis for why light has a maximal velocity. It's the max velocity given by the square root of L over d, or the max velocity is determined by the elasticity L and the density of the ether. So just saying, here we have a rationalization of c, the velocity of light. And energy less than h is a strain in the ether, but no wave. So the ether is strained, but there's no wave. And the instant energy h is received, the elastic limit is surpassed, and we get a wave. So the ether accepts as a limit only the constant quantity h. Given the amount E, the vibrator must affect the ether E over h times per second, equal nu, the wave frequency that the vibrator gives off. So an implication to look at here on the wave packet. We've seen this, and we'll see it worse in the photoelectric effect. The energy E in the packet is proportional to the frequency. So energy is proportional to the frequency, and we'll see this represented as a little packet. Here's a high frequency packet with an amount of energy, a big amount of energy E, and a low frequency packet with a smaller amount of energy E. But for Kessler, each ether wave only contains an E in energy that is a function of h, that is the amount of energy required to hit the elastic limit of the ether medium and send a wave through it. So for a given E, the packet must sum or reflect the smaller E's, energies of, say, 10 waves from a vibrator. So we have the vibrating particles giving off 10 waves, and to reflect that total energy, that particle somehow has to cut off the waves at 10 and embody that energy as the reflective energy of 10 waves. QM is not worried about this. How would packets reflect or sum a frequency? It would be a difficult question. For Kessler, it would be the number of vibrators. You'd have 10 vibrators, all at the same frequency, in phase, and all contributed then to a composite wavefront, therefore a larger amplitude wave. This could simply be a pulse. That is, you could simply take one of the waves, but you'd have a larger amplitude wave equal to the energy of 10 waves, or a series of such pulses. For QM, it appears a vibrator at say frequency equals 10 as above just gives off the entire energy E in one wave, making the packet in just one wave. There we are in our little picture there, QM vibrator, but we just need one wave to give off the energy E with a frequency of 10. So the properties of a propagating medium, not a factor at all in QM. Kessler develops a great number of implications. This is enough to see certain essentials. What a physical embedding of a mathematical constant like h might look like. A glimpse of wave theory for quanta. There are glimpses of resonances and questions in the particle dragging the ether with the ether's vast continuity. A glimmer of QM's strangeness, the superluminal effects, interconnectedness, and non-locality. But what of electromagnetism, EM, of the dielectric and magnetic and their mixture in an EM wave? Is stressing the ether actually stressing the dielectric? How would we relate, say, Maxwell's primitivity of free space, or the permeability, all part of his equation structure, shall we say, for the velocity of an electromagnetic field? Well, Kessler speaks little to EM, and this is all something that would have to be put together someday. But we need now to look at physics' black body explanation in a bit more detail. When you look at the black body narrative, say in Wiki or other current sources, we quickly hit 4 major elements. Something was theoretically existing called the ultraviolet collapse. Then you had the equipartition theorem, then modes and quantization of modes, and the Bose-Einstein statistical distribution. Somewhere in this, we expect to find out this: why does the number of quanta decrease? And was the wave explanation really destroyed? The modes of waves generally refers to the constraint on waveforms in a given space. For example, the modes of a vibrating string of a certain length. There's pictures of modes there, or same thing for a vibrating jump rope, as in the green tied to the wall, and we're swinging it, and we can bring it into certain modes. Always an integral number. Rayleigh and Jeans had derived the number of modes that waves of each frequency can assume in a unit volume, like our black box. The result, that expression 8 pi nu squared over c cubed being the cubical box, nu squared being the square of the frequency. Little picture here. The idea is that more modes can fit in the box, say on the right. You have a higher frequency, more modes are in the box on the right than it can fit in the box on the left. And it's a function of the square of the frequency. So the higher the frequency, the more modes that fit. And the number of modes that fit grows by the square of the frequency of the wave, nu squared. Okay. So then we come to the equipartition theorem. In this theorem, each and every mode in a system at equilibrium has an average energy of kT, T being the temperature. So K is a proportionality constant, saying the energy of a mode is some proportion of the absolute temperature. So in this case, that particular mode for that particular frequency has a certain energy, E, proportional to KT. And there's an equal amount of energy in each mode. So there's another mode. As you can see, it's not the, it's sort of like the top string in the green box there. And then it too has the same amount of energy, again, proportional to KT. So if we flip to the right, we'll see, yes, that also has an amount of energy proportional to KT, that particular mode of that higher frequency. And we take a lower mode, a lesser mode of that same frequency, it too has the same energy, KT. So there's an equal amount of energy in each mode. Okay, now for the catastrophe. This brings us to the UV collapse, or the catastrophe. Since there are an infinite number of modes, this implies infinite heat capacity or infinite energy at any non-zero temperature in the box. An unphysical spectrum of emitted radiation that grows without bound with increasing frequency. So our classical curve there just begins to grow and grow and grow. Note that the energy emitted is growing as a function of the square of the frequency, nu squared, again always being multiplied by the temperature or proportional to the temperature. Or equally, that the energy emitted grows with the number of modes. For the number of modes increases with the square of the frequency. So that rising curve is also the modes rising. So the collapse was, rather than an actual physical event, just a logical problem, which is to say, a consequence of this way of looking at things, the equipartition concept. Certainly not the Kessler way we saw earlier, where our green graph depiction is simply the inverted depiction of the white. That is, it's inverted with respect to the frequency dimension. The green is rising in frequency from right to left, and the white is rising in frequency from left to right. Just an inverted frequency dimension. Same representation in other words. But where in Kessler, that peak shift was occurring as representative groups were heating up, increasingly and then passing into the visible. And this was a function of where these groups were, where the particles were inside the box. This conception that quantum mechanics presents with the modes is an abstract one, difficult to get one's head around, and certainly what Kessler presents as a rather commonsensical, eminently reasonable approach gets, well, shall we say, heavily obscured. So now we come to Planck, and in this standard story of things here, then, it's said that Planck's E equals h nu quantized the number of nodes. So the first thing that happens is infinitesimally small modes are not allowed. And why is that? Because you need an E, or energy, equal to or greater than h to make a wave. So that's nice, but it's the same as Kessler. Remember, you need a certain amount h of energy to make a wave in ether. For high frequencies, you need a huge pile of energy to create a given h nu. I mean, the greater the nu there, the more energy you need. Given nu is a big number of waves, you need a big E. So note, high frequencies are not going to be excluded, but they're getting increasingly less probable in this model. So what we have here when we look at this table is what was essentially a high frequency wave constraint that was applied to this phenomenon. If you note there, looking at the classical and quantum rows, the first column there, same modes per unit frequency, per unit volume, exactly the same. And then the probability, they call it, of occupying modes is equal for all modes, and the average energy per mode is kT. But now, instead of kT, what we've done for each mode is apply this constraint, h nu over h nu e to the kt minus 1, which is to say, as t rises, we're dividing by an ever bigger number. And so there's going to be a punishing factor, shall we say, on energy output gradually as t rises. In other words, the high energy groups here in that our original picture, in the higher frequency ranges, left of the apex of the peak shift, are going to become less and less probable, because as those temperature rise from 600 to 601 to 602 to 603, etc., the constraint is getting stronger and stronger against, well, we'll call these particles vibrating at higher frequencies. So this is kind of interesting, because if we ask, well, how to reduce the particle groups registering at higher frequencies, which is what we're seeing as the peak shifts to the left. In the Kessler world, remember, he argued, well, the bolometer is not registering as groups transition into the visible, that visible energy is being lost because the instrument is not sensitive. And so as more and more groups shift into the visible region and give off visible energy, it's simply not being recorded, and so the energy output is dropping. For QM, we just divide by the rising temperature, essentially. So we're using the temperature rise kind of acutely against itself, so that eventually, as the temperature rises, we're getting less and less output, which seems a little bit ad hoc. In fact, one could kind of ask, well, for Kessler, why not just put a similar temperature-based constraint in, then give up on the bolometer and its sensitivity, if that's not the case, and simply use his model, but put in a nice, cute little constraint with respect to the rising temperature, such that it all works out very nicely to drop the curve. You see, I'm suspecting this is just a little too ad hoc and cute at this point in the QM world. So what we get then is this curve equation where the high frequency wave constraint now appears in Planck's formula that describes these curves. There's that constraint with the KT temperature rise has the operative component in there. So classical modes only multiplied by KT, as we saw on the last slide, the last table. And in the quantum mode, these modes are multiplied by KT embodied in that constraint, thus getting the drop. So given the energy required to form waves or modes with increasing values of the frequency nu, this wave formation becomes increasingly improbable as h nu grows. So energy output from the black body begins to fall. But is any of this incompatible with the wave theory of the black body? That is, with Kessler, at least insofar as he is simply holding that it takes an amount of energy h to form a wave in the ether. With that classical wave theory, particularly in the ultraviolet catastrophe formation, it's simply not considered this possible property of the ether. So when was wave theory and its ether destroyed? Well, the photoelectric effect. The standard view is that Einstein, using Planck's quantum concepts, put the nail in the ether wave coffin with his 1905 paper on explaining the photoelectric effect. This, together with his 1905 special relativity paper, which supposedly explained the Earth's apparent lack of motion in the ether, formed a double whammy. The PE paper started with a view of photons, little packets of light, each of which had or also had an energy proportional to its frequency, or E equals h nu. Though Einstein did not originate this term photon. In fact, he did not even use the word particle. He spoke only in terms of energy localized in space, a fairly vaguish term. The photons were not a propagating wave through a medium, that is, through an ether. They were just little packets, little bullets. Now, those of you that have seen my critique of special relativity, especially as currently interpreted, can understand my paranoia here. I have experienced just what I see as the ubiquitous mind programming of physicists with respect to SR and how it's to be interpreted. It's literally a mind programming. It's rather amazing. Now we add in this ad hoc flavor of Planck on the black body, and I kind of detect mind programming again, that is there something that maybe isn't wearing clothes. So Kessler offered a wave explanation of the PE too. So I think we should look a bit further. So next, the photoelectric effect. Till then, signing off.